Hello, everyone. I am Elaine O'Neill, the Director of Science and Sustainability at CORRIM and an affiliate faculty at the University of Washington in Seattle. CORRIM is the Consortium for Research on Renewable Industrial Materials, a 20-university consortium that has been doing life cycle research on wood products since 1996. As I mentioned in my keynote address on wood as a carbon negative technology, we have taken that data-intensive inquiry into a systems analysis frame loosely based on the circular economy model. Today, I'm sharing a synthesis of the CORRIM workshop on integrating forests and wood products into the circular economy that was held in January 2020 in Seattle, just before the COVID-19 lockdowns. At that workshop, we had representatives from 3 countries and 31 different institutions, trade and research associations, government agencies, consultants, industry representatives, and environmental NGOs. This was the first North American conference to explicitly explore research needs for integrating circular economy concepts and approaches across the life cycle of structural wood products, from forest to frame to end of life and end of use in North America. What exactly do we mean by circular economy? This particular chart endeavors to explain that. It is courtesy of Jennifer Russell from Virginia Tech. She is a CORRIM member and was a keynote speaker at our conference in January. The circular economy is based on several key principles. Number 1 is to design out waste and pollution by developing cascading use streams. So you take the waste from one process and use it in another process. Another core principle is to keep products and material in use. So here you see this example of repairing, reuse, remanufacture. Each one of these takes more and more energy to do, but it will maintain or ensure that that material is retained in use. A third principle is to regenerate natural systems. And finally, the goal is to decouple economic activity from resource consumption. While waste reduction is a goal, the focus is on value retention and value added, which presumably helps make better choices. The dominant circular economy model, as proposed by the Ellen MacArthur Foundation, has 2 flows, the blue stream and the green stream, each with independent cascading use of product and materials based on circular economy principles. So here's your blue stream and here's your green stream. The blue stream reflects flows of non-renewables, those that are mined or extracted and then processed and put into use. Classic example is aluminum, any kind of metal or plastics. This model highlights the goal of having cascading uses after manufacturing to ensure that materials are used and reused efficiently. So here's your cascading uses back to some kind of manufacturing or reuse or sharing economy. The green stream reflects flows of biomaterials, so those things that are grown or farmed. So examples that they commonly use are wheat and fish. They come out of the biosphere, they go into the economy, but they limit the flows to the consumption. These are things that you consume. You eat these things, and then you dispose of them. They go back into the environment as a biosphere, ideally as a biosphere replenishment instead of a waste. So you would want to be thinking about composting as opposed to landfilling, for example. Now, this model does not account for biomaterials that cross over between biological and technical systems throughout their life cycle. The portion I've highlighted in brown, so I've added some little brown arrows in there. While durable wood products like building materials certainly fit into this category of crossover materials, so does bamboo, hemp, and a wide range of textiles, including rayon, cotton, silk, and wool. This crossover effect is a clear shortcoming in the current model, especially for durable wood products used in buildings and construction. So in this, what I've done here is I've zoomed in so you can have a closer look at that model. If you zoom in on the wood pathways, it is perhaps no surprise that the crossover hasn't been addressed. Thinking about value retention and material flow between the green and blue streams exposes a multitude of crossover opportunities, which makes this task both complex and difficult. It also reveals a tremendous number of research opportunities for scientists in the wood, forestry, land use, engineering, architecture, construction, and operations research fields. It's probably a little easier to imagine this cascading use philosophy using a simpler example. This cascading use already exists in a modern sawmill that optimizes the sawing to maximize value and directs waste from the sawing process to various co-product pools or energy streams depending on their highest market value. So here we see that the sawing, the green chips and the green sawdust and the bark and the hog fuel, they all go to different places. Expanding that kind of techno-economic approach to the entire life cycle is the challenge of the circular economy, especially figuring out how to reuse it after the end of its first useful life, which is where the most impactful carbon benefits are likely to accrue. For looking at circularity for durable wood products, we developed a simpler model that we are calling the CORRIM Circular Economy model. Now, since we put it out in January, it's had a few iterations already, but it's a reasonable first pass at framing wood in the circular economy in a way that can daylight the feedbacks and crossover opportunities for wood. Now, the CORRIM model implicitly incorporates carbon flows as a method for tracking wood constituents from the green stream, where the plant is being grown, so it's absorbing that carbon out of the atmosphere, through the blue stream, where it's in that wood product, that building material, and then back to the green stream again, demonstrating the two-way flow of the core molecule of wood. Remember, wood is 50% carbon. We added in this case, we added in a brown stream for the manufacturing and conversion process to capture that complexity. The reason we're looking at this model is because it links back to current measurement methodologies, specifically the definable life stages that correlate to the modules that are used in the North American product category rule for wood products. So in that way, we link it to an economic system that's currently in place and an evaluation and sustainability system that's currently in place. The junctions in this diagram capture the fact that at each of these flow transitions, there are definable and measurable energy inputs and outputs, and the changes in the carbon balance of the system. There's also a change in the form of the product at those stages. Now, at that meeting, we had expertise in every one of the circles in this model at our workshop. And so I want to touch on a few linkages between them. I have heard it said multiple times in the past 2 years that we build the equivalent of a New York City every 35 days when we're measuring worldwide construction. I did a little back of the envelope calculation based on that number because I found it quite stunning. If we keep building out instead of up, that is the conversion of nearly 303 square miles, which is the size of New York City, of potentially arable land for growing crops or forests that are removed from production every 35 days. That's about 817,000 hectares of land under asphalt and concrete every year, land that could be growing trees or food. Now keep in mind, I wasn't measuring infill here. I was just looking at worst case scenario. To put that in perspective, if that land were in the Pacific Northwest West Side forests where I am now, it would be sequestering an average of 8 tons per hectare per year of carbon under commercial forest management. So that New York City size loss of land would be equivalent to losing about 6.5 million tons of biomass, 3.25 million tons of carbon, or nearly 12 million tons of carbon sequestration potential per year if it were concentrated here in the Pacific Northwest, which happens to be one of the most productive forest regions in the world. Now, obviously, in other regions, like I looked in the Northeast, it's much less than that. But regardless, if we look through the lens of land use, continuing to build the way that we have always done is like shooting ourselves in the foot. On the other end of the forest wood product and use continuum is how we use the wood we do produce. Alan Organsky, a practicing architect and senior critic at Yale School of Architecture, also spoke at the conference. And he spoke of the opportunity to mitigate the enormous carbon footprint of the built environment, even with the double specter of climate change and population growth, by building with wood. This is his figure here. This was presented as a feasible technical solution if we imagine a new way of building that resulted in cities becoming carbon sinks instead of carbon sources. The change would incorporate mass timber wood products, some of which have proven themselves over nearly 100 years. But more importantly, his proposed approach would alter our building morphologies and city density, exactly what I just mentioned in the land use side. His estimate, as shown on this slide, was a 23-fold increase in carbon stored in the built environment per hectare of land consumed, just by changing these building morphologies and densities. Taken together, these two ends of the spectrum address the challenge of land use and land use efficiency, which leads to a core outcome of the conference. In order to move fully into a circular economy, there needs to be much better integration and cross-linkages throughout the supply chain. And logically, the change from a linear economy to a circular economy starts with the creation of a circular knowledge network that links downstream users to upstream processes in a streamlined and coherent manner. This can best be illustrated by an interconnecting buckyball. Here I show Alan Organsky's first estimate of the disciplines involved in black, and those that were added during our workshop discussions in red. There's a lot of opportunity for integration and overlap amongst all these systems. There were 5 main research themes that emerged from the conference. Number 1 was developing a circular economy model that works for biomaterials, looking at data needs, data synthesis, and data transparency. We need to get a handle on what's happening after the end of the first life. We need to look at sustainability of forests and businesses, and we need to think about systems analysis. You have to keep in mind there was a tremendous amount of crossover between these topics as they feed forward and backward within the system, but this seemed like a logical way to aggregate what we talked about over that very intense 2 days. The first theme relates to developing a circular economy model that works for biomaterials in general and durable wood products in particular. It would need to, at a minimum, address the crossover effect and ideally could be used to daylight the material flows and cascading uses and the opportunities for improvement within the current system and some projections about the future. Decision-making tools would naturally emerge from such analysis. The second theme was around data needs, data synthesis, and data transparency. There were many data needs identified throughout the supply chain. Specific requirements for updated data on housing stocks and stock changes, demolition rates, landfilling rates, energy recovery, construction waste were considered critical for understanding wood flows in the blue stream. There was also a great need for a wood inventory, including inflows and outflows that would expand the blue stream to include some combination of forest stock and flow data, construction and demolition waste flows, imports, exports, and non-structural uses, including uses for fiber for paper, textiles, chemicals, non-traditional uses like cement binder, and energy. I think some or most of this data currently exists in some form, but it's dispersed and fragmented, so data management tools are needed. We talked about the need to quantify uncertainties in our estimation procedures, and even had a bit of fun talking about the future of QR codes for pieces of wood. We really don't know much about what happens after the end of life. Estimates are that 30% of the current housing stock will be demolished by 2050. It will be critical to identify how much of the material in the current building stock, what we call building stock forest, is usable, at what cost, and at what benefit. There is a need to document the design, how it was engineered, and why, to ensure that the materials can be reusable, consistent with the safety, structural, and technology needs of the future when the building may be deconstructed for reuse. Experts on designing for disassembly highlighted some manufacturing processes that are likely to be problematic in the future, suggesting opportunities for material development research. Significant work is needed to simplify information on forestry, the forest sector, and the relationship between forest use and forest sustainability. This was needed for design teams, policymakers, and the public to garner some social license for the kinds of work, the kinds of potential there is in this forestry to product to in-use continuum. A core element of forest sustainability as it pertains to providing wood to the economy requires keeping forest land as active working forests, especially in the face of significant population growth. Maintaining forest land matters globally and nationally, but is most critical at the regional scale because that scale matters given the relationship between maintaining working forest and a sustainable, profitable milling infrastructure. There is also a need to characterize the sustainability of different kinds of biomass appropriately. That biomass might be farmed, as in tree farms, or opportunistic wood recovery from residues, or harvested to create co-benefits like fire risk reduction in the West. Each of these sources of fiber will have a different value proposition that needs to be incorporated into circular economy thinking. And finally, systems analysis really incorporates the other themes, but sits at a scale that is larger than all of them and deserves its own mention. In essence, all this work will ultimately require integration and identification of areas of improvement. But to start, we need to establish a baseline that provides the material flow at the present time. There will be obvious gaps in that material flow and therefore many opportunities to research barriers to circularity from a variety of perspectives, including from the economic perspective, institutional and legal perspectives, and technical life cycle perspectives. Overall, the research opportunities are plentiful and the need to move forward is great. I'm going to give the last words of the day to an idea that Alan Organsky presented near the close of his presentation in January. He said something like this: "We spent the first part of our history here on Earth living in harmony with the natural system, sort of in balance, in a carbon balance, and the past 350 years or so digging a big hole in the ground by continuously mining materials to meet our needs and spewing more and more carbon into our atmosphere. The vision of our future does not have to be an even deeper hole. We have enough information now to know there are ways to replenish our carbon pools by using bio-based construction materials to meet our needs without going back to the dark ages in terms of our economy. To do that will take concerted effort on the part of scientists, engineers, policy makers, and builders to create the linkages needed to make the dream of a circular economy a reality. The workshop and its outcomes was our first step on that path for wood, but it's certainly not our last." Thank you.